I was recently implementing eager bidirectional attention for the first time, and understanding the attention mask was the most difficult part of the implementation for me. And once I understood how the attention mask worked, that actually unlocked my understanding of the rest of the attention mechanism implementation. So in this video, I'm going to start by focusing on what I learned about the attention mask and how I got a better understanding of that. And then I'm going to use that to expand my explanation of the entire eager bidirectional attention implementation. So the final slide will be my full code showing how I've implemented this mechanism. Here are some parameters that I'm going to define from the get-go. The batch size is 4 and the sequence length is 16. There are 8 heads, each with a head dimension of 32, and the hidden dimension is the product of those two, which is 256. The ones I've highlighted here, batch size, sequence length, and num heads, those are the dimensions of importance for the attention scores, which we'll see later on. So this is what my attention mask looks like. I have 4 items in the batch, and I have 16 tokens in each item because that's my sequence length. So this is a 4x16 tensor. And anywhere that I see false, let's just assume those are padding tokens, so I want to ignore those. Everywhere that I see true are non-padding tokens. So the first item in my batch has 12 non-padding tokens and 4 padding tokens. The next item has 6 padding tokens. The next one has 8, and the final one has 11. What I'm trying to get to is an attention shape of 4 by 8 by 16 by 16. The most intuitive part is this 16 by 16 because each of the 16 tokens are potentially attending to each of the other 16 tokens. So I know that 16 by 16 has to be next to each other. And then I have 8 heads, so each attention head is going to have its own 16 by 16 matrix of attention scores. And then I have 4 items in the batch, and as we see here, because there's a different number of padding tokens for each item, I'm going to have my own set of attention scores for each item. So how do I go from a 4 by 16 to a 4 by 8 by 16 by 16 tensor? So torch.tensor.expand is the first method that we're going to use, and this returns a new view of the self-tensor with singleton dimensions expanded to a larger size. And expanding a tensor does not allocate new memory, but only creates a new view on the existing tensor where a dimension of size 1 is expanded to a larger size. So the way I kind of understood this is like broadcasting. So it's kind of broadcasting these dimensions, one dimension to another dimension based on the size that you provide it. So the first thing I'm going to do is I'm going to go from a 4 by 16 to a 4 by 8 by 16. So what this is intuitively, or I guess semantically, what this means is that I'm going from having a single tensor 4 by 16 to one of those 4 by 16s for each of my 8 attention heads. So the first thing I'm going to do is I'm going to add a unit axis as a second dimension. So I'm doing mask.unsqueeze1. So that would give me 4, 1, 16. And then I'm going to expand by keeping the 4 and the 16 in place. But now I'm going to expand this unit axis in the middle to the number of heads, which is 8. So the result of this is now I have a mask that's shaped 4 by 8 by 16. And basically what this means is that I've expanded my 4 by 16 across the 8 heads. So we're going to look at this a couple different ways. The first way is I'm just going to look at one of these 4 items, and one of these 4 items has an 8 by 16 tensor. So if I look at the first item, which is index 0, what I see is I see my first item in the mask with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 true values and 4 false values. I see that tensor, that 16 element tensor, repeated 8 times. So how I interpret this is that I'm basically seeing that single item's mask projected across my 8 attention. If I look at the second item, that corresponds to the second mask tensor here, with its 6 false values. Third item has 8 values that are false, and the fourth and last item has 11 false values. So in this way, I can see that it's basically copied over each of these items across my 8 attention heads. However, that was not the most intuitive way of seeing it, although it was, helpful to kind of get me started. What I ended up finding the most intuitive or most interpretable was that I take all of my batch items, so all 4, and then I just look at the first attention head. So here I'm looking at all 4 here, and then instead of all 8, I'm just looking at one of these, so the 0th item, and then I'm looking at all 16 items in the sequence. And this now makes sense. So now I have my mask, my 4x16 mask is what we see here for the first head. And in this way, if we look at the second, third, fourth, fifth, etc. head, we would see that the 4x16 mask is applied to each head. So this makes sense now. It's basically taken my 4x16 mask and it's copied it over to all 8 heads in this second dimension. So here's a visual of looking at these 3 dimensions. And the magenta is my original mask, and I've copied that over 8 times. So that's the dimension 8 here. Dimension 4 is unchanged from the original mask. That's the number of items I have. Dimension 16 is unchanged. That's the number of tokens I have in the sequence. So that was the first step. That was not the final shape that we want. What we want is we want a mask that matches the attention shape. And the attention shape is 4x8x16x16. So in addition to adding a unit axis at the second dimension, we're going to also add a unit axis at the end. So after the unsqueeze calls, this would be 4, 1, 16, 1. And then I'm expanding that. I'm keeping the first dimension the same, and I'm keeping the first 16 the same, and then I'm expanding everything else to 8 attention heads, and then I'm expanding everything else here to the sequence length of 16. So after this expand, I get 4x8x16x16. So what am I looking at here? I'm looking at all 4 items in the batch. I'm looking at the first attention head. I'm looking at all 16 items in my sequence length. And then I'm looking at the first of the 16 items in this second sequence length dimension. So this is what I see. And this is my original mask. So another way to think about this is that my original mask is being copied over across 8 heads, but it's also being copied over across the dimension of 16, which is the sequence length. It's a little harder to visualize this, so I didn't visualize this with a visual like this one here. But instead, what I'm going to do is I'm going to look at the entire 16x16 tensor, which kind of represents the attention scores for that batch item and for that attention head. So here I've indexed the 0th item in my batch and my 0th item in my number of heads, which is 8 total. And then I've looked at my 16x16 matrix, which is going to correspond to the 16x16 matrix of attention scores. And what I see here is I see in column form, it has copied over my first mask item, which has 4 falses. It has copied that over 16 times in 16 columns. So here's 4 falses in each column, and there's 16 of those. So there's 16 items as we go horizontally across the columns, and there's 16 items as we go vertically down the rows. If I look at the first item, or I guess the second item corresponding to index 1 in the batch, I can see now this is my 6 false values. So I see my 6 false values here, copied across 16 times. Here's the third value with 8 false items. And then here's the fourth item in the batch, which has 11 false elements. And so I can see that my 16x16 matrix has the same mask for a given sequence, but it's now repeated 16 times across the columns. So what am I going to do with this? Now I can actually apply the mask. So I'm going to make a fake attention score matrix. It's going to be just shaped just like the mask, except I'm just going to have ones. And then I'm going to use torch.where so that where the mask is false, I'm going to replace the attention value of 1 with a negative infinity value. And where it's not false, so where it's true, I'm just going to have the attention value. And so I'm printing the first item and the first attention head and 16 by 16 of my attention scores. And this is what I see. So I see the first 12 rows have ones because that's where mask is true. And the last 4 rows all have negative infinity because that's where the mask was false. And that's what we see up here. Last 4 items are false. So what happens to these attention scores? They eventually go through a softmax operation. And what the softmax does is that for each value in the given dimension, it takes the exponentiation of that value divided by the sum of exponentiation of all of those values in that dimension. So I pass my attention through the softmax. The dimension I provided is -1, so it's that final 16 sequence length dimension, which is the columns in this case. And so what it's going to do is that it's going to go across the columns, so it's going to go through each row, and it's going to calculate the exponentiation of that value, sum it up, and then for each value up here, it's going to calculate the exponentiation and divide it by the sum. The problem in this approach is that if we look back here, all of the values in these final 4 rows are negative infinity. And so what happens here is that we end up dividing by 0, so we get not a number. So obviously this is not what we want. So mathematically, this doesn't work given how I've set up everything here in terms of all the shapes and the dimensions. So what we're going to do is we're going to swap the last 2 dimensions of 16. So the shape is still going to be 4 by 8 by 16 by 16, except now my false values are projected horizontally. Or another way to think about it is that the mask sequence is now copied down the rows, whereas before the mask sequence was copied across the columns. So that's what permute does. Instead of 0, 1, 2, 3, I have 0, 1, 3, 2. I'm basically doing a transpose across the last 2 dimensions. And so I can see now that all of my rows have some true values. So I apply the mask to the matrix of ones of attention, and where the mask is false, I put a float of negative infinity. And if I look at this now, each row has some ones and it has some negative infinities. So when I take the softmax across the columns, so the denominator has the sum of the exponentiations of each of the elements in the rows, now I correctly have zeros and not a numbers. So this was the first kind of explanation that I understood, which was the mathematical one, that the reason this previous shape for the mask was incorrect was because it was leading to full rows of negative infinity, and that was leading me to not a number values because the denominator in the softmax was 0. And when I transpose the last 2 dimensions, now I have some true values in every row. And so that means when I take the softmax across a dimension equals -1, I get 0 or more as my values. So mathematically, this works. But there's more ways to think about this. So the question I wanted to ask after this was that, like, what do the rows and columns of the attention scores mean? So I understand that mathematically, because of the denominator, the softmax, the rows cannot have all negative infinity values. But what does it mean in terms of like the concept of attention that is actually happening between these tokens? So to answer that question, we have to go back to this fact that attention scores are between tokens. So we need 2 dimensions to be 16 by 16. And we have to figure out how to arrange everything else so that we end up with attention scores that have a 16 by 16 set of consecutive dimensions. So in my case, let's assume that our QKV input shapes are batch size by sequence length by hidden dimension. So 4 by 16 by 256. We then use the view method on the tensor to break up that 256 into number of heads, which is 8, by head dimension, which is 32. So I do q.view, k.view, v.view. And so I'm splitting up the total hidden dimension into the number of heads with each head dimension. So those have to be the head dimension, the hidden dimension has to be divisible by the head dimension. And then when I look at the attention formula, I'm taking Q matrix, multiplying it by the K transpose. So what that means is I'm going to have Q times K transpose, and that's going to equal my attention scores. So whatever dimensions are being multiplied here, they have to end up with something that has a 16 by 16. And so this is how I was using what I know that attention happens between tokens. So, and I know that the sequence length is 16, so I know that there has to be a 16 by 16 dimension. So I'm using that as a starting point and then reverse engineering what the other shapes need to look like to get this desired result. So one such shape that works is I have my Q matrix or Q tensor, which is 4 by 8 by 16 by 32, and then K transpose. So K itself is going to also be 4 by 8 by 16 by 32, but we're going to transpose the last two dimensions to get 4 by 8 by 32 by 16. And when we matrix multiply these two, matrix multiply these two matrices, 4-dimensional by 4-dimensional, the first two dimensions stay the same. So we have 4 by 8. The 16 by 32 times 32 by 16 gives us a 16 by 16 set of attention scores. And I know that attention is between tokens. 16 is my sequence length, so I know I have to end up with something with a 16 by 16. So this let me know, okay, I'm on the right track. So how do we get here? Well, if we look at the original shape, we have batch size, sequence length, number of heads, head dimension. I could have done the view differently, but I think this is the right way to do it because the last dimension of 256 is being split up into 8 by 32. So maybe there's not another way to do this with view. But because that's the dimensions I have, 4 by 16 by 8 by 32, and because what I want is 4 by 8 by 16 by 32, I'm going to swap the 16 and the 8. So again, we use permute, and I'm going to say instead of 0, 1, 2, 3, give me 0, 2, 1, 3. So the third dimension here, 8, gets moved to the second dimension. The second dimension, 16, gets moved to the third dimension. So what is my result? 4 by 8 by 16 by 32. And that 16 by 32 is what I'm looking to get. Now that I have my K as 4 by 8 by 16 by 32, I'm going to transpose the last two dimensions. So I'm going to, instead of having the second to last and the last, I'm going to have the last and then the second to last. So instead of 16 by 32, I'm going to swap them and I'm going to have 32 by 16. This negative 2 corresponds to the second to last, which is the 16. This negative 1 corresponds to the very last dimension, which is 32. So now I have what I need. I can multiply Q, and now I get 16 by 32 times 32 by 16, which gives me the attention scores of 16 by 16. So now we go back to this question. What do the rows and columns of the attention scores mean? Well, let's look at how we built up the attention score matrix. We started with Q as the first matrix, and then we had K transposed as the second matrix. So when we do matrix multiplication, we're going to start out with these 16 rows, and we're going to line those up with these 16 columns, except these 16 columns started out as rows of our key matrix K. So our final result is that the rows correspond, in the attention scores, correspond to the rows of the query matrix, and the columns correspond to the key rows. So taking a look visually, these are my query rows, and these are my key rows. And the key, pun intended, idea is that my queries attend to my keys. So I'm going in with my queries, and then I'm going across my keys, and I'm attending to each of those tokens given my query vector. So let's go back to what our mask meant. Anytime we have a true in our mask indicates we want those tokens to be attended to. Anytime we have a false means that we have masked positions. We don't want these tokens to be attended to. So let's look at my first iteration of my mask. I unsqueezed and I expanded it, so it was 4 by 8 by 16 by 16. But if we look at this idea that the rows are queries and the columns are keys and the rows are attending to the columns, we can see that even though I've blocked off here in my mask the last 4 tokens, these tokens are currently incorrectly being attended to. And what's happening down here is that these query vectors, which correspond to the false tokens or the masked tokens, they are not attending to all the tokens. And that's not our goal. The mask of false doesn't mean that that token does not attend to other tokens. The false means that that token is not being attended to. So in another way of looking at it, once we fix this dimension by permute, so we go from 0, 1, 2, 3 to 0, 1, 3, 2, now we have the correct columns that have the negative infinity. So the mask tokens are correctly not being attended to. So query vector 0, which is this first row here, it attends to the first 12 tokens, but then it does not attend to the masked tokens. Same thing here, this query down here attends to the first 12 tokens, does not attend to the last 4. So where the negative infinity values are, at least with how everything is set up here, given that queries, the rows, attend to the keys, the columns, I don't want my rows to have negative infinity because those correspond to the queries, the things that are doing the attending. I want my columns to be negative infinity because those are my keys, the things that are being attended to. So in addition to mathematically working out, I found this understanding or this interpretation to complement that. So it's not just the mathematical reason that the softmax needs to work. It's also the concept of queries attending to keys and those keys being blocked out because we don't want them to be attended to. So this is a summary plus a couple more lines of my final implementation. I start out with a query vector as well as my key and value vectors or tensors that are bat size by sequence length by hidden dim, so 4 by 16 by 256. I use view to split that 256 into 8 by 32. I swap the middle dimensions so that now I get 4 by 8 by 16 by 32, so I can isolate this 16 in my attention scores. I then do matrix multiplication between Q and K transpose, so 16 by 32 times 32 by 16, the 32s cancel out, and we end up with 4 by 8 by 16 by 16. If mask is not none, then I'm going to reshape the mask and expand it so that it's 4 by 8 by 16 by 16, and I'm going to permute the last 2 dimensions so that number 1, the softmax calculation works, and number 2, I'm correctly interpreting the mask tokens so it blocks out those key columns that we don't want them to be attended to. I apply the mask to my attention scores, so where the mask is false, I give it a negative infinity so that when it goes through softmax, e to the negative infinity is 1 over e to the infinity, which is 0. I apply softmax to the last dimension, so each row will add up to 1. So each query is attending to all of the keys, or all of the key tokens, and the sum across that row is 1.0. I matrix multiply attention by the values. I permute this so that I can get my num heads and hidden dimension back at the end, and then I reshape it so I can combine 8 by 32 to get my hidden dimension of 256, and then I return my attention scores, or attention matrix. So that is in a nutshell how I understood the eager bidirectional attention mechanism implementation. I started out by realizing I didn't understand how this mask needed to be reshaped. And then once I figured it out, I didn't really understand why it worked. I just knew it worked because it passed the test. So I went back and I understood why the mask is being reshaped in the way it is to match the dimensions, what they all look like, given those different visualizations of true and false values. And then I zoomed out again and thought about it more conceptually, that the reason we need that particular arrangement of 16 by 16 is because the queries correspond to the rows and the keys correspond to the columns. That's part one. Part two is that queries are attending to the keys, and false values in the mask means those tokens should not be attended to, which means those columns should not be attended to. And of course, the math works out, conceptually it works out, and I get the correct final attention matrix. So that is my recap of how I understood eager bidirectional attention. I will be probably doing some more videos on attention mechanism related items, especially flash attention, as I understand that more. So please subscribe, also like and comment, etc. And I will see you next time.